Hello and welcome back to my channel, Afshar-Aykin Tech, where I go over software, electronics, and interfaces between the two and how to on drone technology. I'm a volunteer firefighter. My name is Aykin. I'm also a self-employed engineer who is currently working on fire technology independently. I am here to share my status update on my drone core system, which is both meant to be manned and unmanned. So the same device will be able to be body worn as a personnel accountability device with imaging, GPS, geolocation, triangulation, a lot of services, as well as being mounted on a drone. Same unit can be either body worn or drone mounted to use to control a drone with more sensors, more attachments, even tool attachments as a possibility, such as saws, hydraulic tools, whatever you may attach to the front of such. So I'm going to go through what I have together so far as a drone core, since I just filed for my patent. It's pending right now, so I have some protections, so I can disclose this now without worrying about anything. Here is basically my setup for the drone core, which now currently includes thermal imaging, GPS, and radio control linked to a controller. I'm going to show the drone core unhoused, assembling it while explaining along the way. Here's the power supply. There's battery terminals here. There's the 5-volt mil-spec power supply here for USB digital logic, which is isolated from the 12 volts, so they have separate grounds. Now, the 12 volts also powers the video transmitters, which are also galvanically isolated, which I will show later how I did that, how to keep the grounds separate. So the core of my drone is a Raspberry Pi 4B. Now, don't get intimidated by this. This is just a hat soldered on top to make some connections with GPS and the radio transceiver a little bit easier and a little bit more compact for when I do need to house it in a box. Now, this is all wired with Teflon wiring, and I used mil-spec or high-grade components where I could. Now, I will show some of the assembly process. Here is an RS-232 adapter. It adapts it to TTL serial. It's soldered to the first serial ports, UART1 on Raspberry Pi 4B. You can look at the pinouts. The radio is soldered directly to UART2, which is the second UART serial port on this. That's soldered to this socket. There's no conversion from RS-232, unlike GPS. High-end GPSs, like this Garmin, usually run on RS-232, RS-485, or some other serial logic that's a little bit older, like the old-style VGA monitors for computers with that trapezoidal connector. Same one right here. You can see it. So that's the same style of logic. So I'm just using a converter to convert it to the serial port that Raspberry Pi does. So when I plugged it in, I plug in the power source here, the USB-C connector, into the Raspberry Pi. So that's my digital logic power source. That's isolated from the 12 volts because you don't want to damage the digital logic device. When I want to snap in the GPS component, I've got two parts here because I want an external connector, because this GPS has an internal antenna. An integrated antenna is made out of thermoplastic, so it's meant for high temperature and harsh environments already. So I'm using a waterproof Deutsch DT series connector here. That snaps together for the outside. Here, a click. There we go. Now on the inside, I'm using a smaller connector. You can use whatever one you want there. I use, I think, JST-PH series. They're these interlocking pins and socket series. So that snaps together there. This is just extra connectors to make it assembly and disassembly easier. For video, I've got a transformer for isolation so that it doesn't share a ground. This does not, the digital logic circuit, 5 volts, does not share a ground with the 12 volts used to power the transmitters. So how I connect it is that the Raspberry Pi 4B, one of the reasons I bought it was that it has a dedicated AUX port. So it's got a dedicated AV port with video. I soldered an an AV connector. It's just a 4-ring jack that has video on it to a BNC connector, which is a twist lock coaxial cable that snaps in there. Now, this goes into the input of the video transformer. Video transformer isolates it. It basically is just a transformer that operates at higher frequencies that video operates at. I think it's 4 to 5 megahertz that video signal is at, analog video signal. And that takes 12 volt source because the transmitters use higher power because they're analog. I'm using analog video for my video transmission. That plugs directly into the battery, so piggybacks right off that terminal. It does not go through the isolated power source. It's isolated from the video, the digital logic side, by the transformer. That's how I maintain the two grounds separate. Now, the two transmitters, I'm using 2 bands, are 5.8 gigs and 1.2 gigs. 1.2 gigs has a little bit longer range, but has less channels that can be used. That would be used in a Mayday scenario or for emergency video traffic of some sort, either manned or unmanned, like a RIT team communication or something of that sort. So I would reserve the 1.2 if I were to decide. I would say that would be for emergency transmissions. So that snaps in here into the video transformer board right here that I soldered together. That snaps in like this, the block terminals. And the last step that I have this Raspberry Pi configured to auto launch is a Seek thermal camera cord. It's basically a USB dongle, but just firefighting or high grade. It's 25 frames per second, 320 by 240 pixels. That plugs in here. So now you can see the camera right here. I'm going to fire it up, and I'm going to show it on 2 different screens at 2 different frequencies, the thermal imaging, and then I will show you on my laptop remote desktoping into the Raspberry Pi. And one last thing that I forgot to attach with that was the radio on top. That goes in this way, into this slot that's soldered on for it. That's to link it to the remote control. So after this, I'm going to show the video on 2 different screens. A wide screen for external use, like if you had a remote command station, and I'm going to show you it on a small portable screen for 5.8 gigs. And I will also show the GPS and the thermal in operation. So I now have the video playing over 2 channels of analog as well as I'm remote desktoped in. So technically that's a backup PID channel for short range for maintenance for digital Wi-Fi. The one on the screen that you see there is the 1.2 gigahertz transmitter is transmitting to that. It's got some interference on it. It's been finicky, this transmitter, since I've replaced it. This is the receiver end. Now, 5G's analog looks like this. It's just not centered right now at the moment, as you can see that. And here it is remote desktoped. And for confirmation, Yes, it is me. So, um, now the thing that I wired for the reason why I wired two video transmitters on different channels on two different bands, is both for redundancy as well as that they've got different advantages and disadvantages. 1.2 gigs has only about 8-9 channels, but has miles and miles of range. 5.8 gigahertz analog is a lot shorter range. It's used by most recreational drone enthusiasts, but it has like 40 something channels. So this would be for every what do you call it, routine everyday traffic at a fire scene, whereas this would be, I would reserve it for, the best example would be at Mayday, for where everybody on the scene wants to tune to the view of a single firefighter's point of view if it's in body worn mode, or if there's something important that needs to be addressed with an unmanned model. Now, the thing about these is that they're independent. So if I disconnect the 5G right here, if I disconnect 5G, that goes black. But the screen for 1.2G stays on. Sorry, there's some interference, but bear with me. Now, if I reconnect this stays on, but if I disconnect 5G, that stays on. So basically, it's a redundancy feature. So if one channel goes out, the other one still functions, as well as I would use them for different functions on the fire ground. That would be my preference. So now we will move on to remote desktoping into the Raspberry Pi, so that we can access the GPS and the RF for this controller here to give the coordinates of to relay the coordinates of the controller. So here I will briefly cover accessing the GPS and the interface between the software and the electronic hardware that I soldered together. I'm going to remote into the command line via SSH for Raspberry Pi, the Linux command terminal. Now I'm going to log in with my username and password. It doesn't show the password in Linux as anything. So I'm going to look up open ports with the dmessage command and look for serial TTY ports. So we know port 1, which is TTY AMA 0, is my GPS that I soldered in place, and TTY AMA 1 is port 2, which is where the RF link for the remote control telemetry, relaying coordinates, and also for RSSI triangulation, which is a backup location for GPS, come from. So first I'm going to read directly from the GPS port, TTY AMA 0. Oh, sorry, it's /dev. It's under the dev folder in the Linux architecture, TTY AMA 0, and then you have to set the baud rate at 4800. 4800 is the stock for Garmin GPS dongles. Now you got a raw GPS feed. I am going to redact the minutes and seconds for privacy, but you can see the degrees on the coordinates. Now I'm going to end that. Now I'm going to do the same command with the remote control, but wait to switch it on for a second. So while the remote control is off, nothing comes through. It's a blank screen. But when the remote control is switched on, it starts receiving coordinates from the joystick. Now, if I start playing with the joysticks, you'll see the numbers change. Those are the X and Y coordinates of my 4 joysticks. Now, on the side of it, I have a small trigger switch. As I slowly depress that trigger, like a saw throttle, you'll see that number at the end climb towards 1. That would be my throttle for, let's say, a saw attachment to a drone or some other power tool.
And the number after the list of coordinates in the curly braces that you see, the -22, -16, -20, is the RSSI. That's the received radio signal strength index. That can be used with 3 or more receivers to triangulate the location of a radio. It's how cell phones can be triangulated even if location services are turned off and GPS is switched off. This is an extra redundancy to my GPS and can be used in a fire where GPS may fail indoors or in a basement. I get good GPS in my basement, but things could go south in a fire really quickly. It's another way to locate, for example, a downed firefighter would be the best example, or a drone that's being used to set a waypoint in the fire. For example, a ground drone that's paired with an individual. I hope you enjoyed my video. I'd like to give a shout out to my lovely wife, who's my camera woman and my partner in this, and partner in everything else. And I hope that everybody had a happy holidays. And this is my status update now that I can publish this since I do have a patent pending protection. Hope everybody enjoyed this video. Until next time, have a good day.